Hello everyone, my name is Khalid Ahmed. I am the CEO and CTO of Taraz Technologies. Before Taraz, I worked as a power electronics researcher for around 8 years at Qatar University and Texas A&M University. I was what you call the hardware guy. I used to build the power electronics experimental setups for our research. Like many of you, we also faced many challenges, and it took us a lot of time to complete the projects. So the typical process we follow with power electronics research is a serial one. We start first with the simulation, either in software or with the help of a real-time simulator, which can be much faster. Once the simulation is up and running, we use a rapid control prototyping device to prototype the control system and test it first with the hill simulator. At this stage, a new set of problems will arise. For example, when you move from simulation to hill validation, the measurement noise can affect the control system. In one of our projects, we used model predictive control. We were measuring the capacitor voltage to calculate the energy it stores using the half CV square formula. At 600 volt average capacitor voltage, imagine how much energy ripple we had with only 1 volt of noise ripple. In the third stage, we replaced the hill simulator with actual power electronics hardware. This is also important because our simulation may not include the physical component nonlinearities. For example, a powder core inductor changes inductance based on the instantaneous value of the current. So this is very challenging to duplicate in a simulation. Finally, if our goal is to make a product, then we have to replace the RCP with an embedded controller. This is also another game. So the C code programming will be much different from the MATLAB blocks that you might be using with the RCP. And therefore the hill validation is done first. At this stage, you may also realize that the embedded controller is not as powerful as state-of-the-art RCP that you are using, and you have to tweak some of the algorithms. Once the embedded controller hill validation is done too, we would like to test it with the power electronics hardware to make sure our embedded controller is stable with the hardware nonlinearities as well. Whenever we discover a new issue, we may want to go back to the previous stage to solve it. This, however, may not be easy. Each stage have a different setup and wiring, and it takes a lot of time to change the setup. Sometimes you have to go back to the hill validation because you may not be able to create some load or source conditions in the real world. For example, if you do not have a grid simulator, you cannot test voltage right through capability or phase imbalance condition without the hill simulation. Also, you may want your development to be more agile. For example, you may want to test and validate each block of the system separately instead of validating the whole system at once. This would require more frequent changes between the validation stages. So this is what we wanted to solve. We wanted a system that can change seamlessly between the different validation stages and without any hardware or wiring changes to the setup. Hence, we created the PELab, the Power Electronics Rapid Development System. So what is a PELab? The PELab is an integrated power electronics development system that can interface to multiple controllers and a hill simulator at the same time. It includes power modules, inductors, EMC filters, relays, and all the required measurements. At the same time, an embedded controller based on the ARM architecture is included as well. As you can see, the system construction is quite modular. We use existing standalone products to build the system. So to summarize the system connections, the PELab basically connects to a real-time hill simulator, an RCP, and to the loads and sources. So what does the interface card do? It multiplexes 3 controllers to 2 targets. Either the real-time simulator, the RCP, or the internal embedded controller can generate the PWM signals, and those signals are routed to a real-time simulator in hill mode, or to the actual Power Electronics hardware inside the PELab in power mode. The analog measurements also come from either actual sensors in power mode or from the hill simulator in hill mode. We designed the PELab to have a very practical and user-friendly interface. A maximum 16 channels each of analog and digital inputs and outputs can be connected to the PELab. So the DB37 connectors are used to connect to the OPAL-RT real-time simulator. The DB50 connectors are used for external controllers and RCPs. The BNC connectors are used for monitoring the system measurements with full galvanic isolation, so you do not need any external voltage or current probe. Also, in hill mode, the analog signals come from the hill simulator instead of the sensors. You can find the analog channels mapping and sensitivity information on the label. The mode selection knob is used to seamlessly shift between the different validation stages of the R&D cycle. We also added dedicated hardware protections in the PELab. The protections include overcurrent protections on the outputs, over voltage protections on the DC links, over temperature protections on the power modules, and short circuit protections on the switches. We also kept the option for disabling most of the protections. This is required for some loads and topologies. For example, if you are working with the motor drive, shutting down the inverter suddenly can cause an overvoltage condition on the DC link due to the back EMF. In this case, you want the controller to systematically shut down the inverter with a ramp down instead of the hard shutdown that is provided by the protection logic. The embedded controller, which we call the PEController, enables you to have a graphical user interface. Also, to make the PELab an independent unit without using any external controllers. It also supports multiple communication protocols. Finally, a cutoff switch will be useful for turning on or off your loads and sources. The rear panel have the power connections. The internal modules are connected to the banana connectors separately, which gives us the flexibility to create the application circuit we want. So these internal modules are configurable. The labels define which power modules, inductors, and filters are installed in the PELab with the respective connectors. The cutoff switch has 6 poles. You can route your power supply or load or both of them through the switch. We also included optional voltage and current sensors to the rear panel. These sensors will give you the flexibility to monitor loads and sources at desired nodes. The PEController is based on STM32H745 microcontroller from ST, which is a dual-core ARM Cortex M7 and M4 operating at 480 MHz and 240 MHz respectively. We also added a 5-inch touch display for the user interface. The PEController can monitor up to 16 analog channels with plus minus 10 volt inputs at 16-bit resolution. All the channels are also simultaneously sampled, and the maximum speed can go up to 250 kilosamples per second. Similarly, a 16 channel each of digital inputs and outputs are supported, and all of the outputs are PWM capable. We also designed the PEController to be an industrial controller, so communication protocols such as LAN, CAN, and RS485 are added. Also, an isolated fiber optic or sync communication can be used for controller to controller communication with up to 50 megabaud speed. This is also very useful to implement master-slave control or develop a distributed control system between multiple PELabs. There are also two USB ports, one for data sharing and the other for the in-circuit programming and debugging. So at this point, you must be very bored. My colleague Hamza Tariq will try to spice things up with a little demonstration video.
Hello guys, my name is Hamza Tariq, an applications engineer at Topologies, and I'm going to be introducing the PELab system. This is a PELab in 6-phase configuration, on top of which is an OPAL-RT real-time hill simulator. I'm going to demonstrate to you how easy it is to go from hill validation to hardware validation using the PELab system. For this purpose, we are using a test topology. We usually use this topology to test the PELab and ensure that everything is working fine after the production. This topology uses 3-phase inductors in Y configuration as loads, and the power converter is a simple 3-phase inverter. You can configure the test topology using the banana connectors and make required connections on the rear panel. Currently, we are working in hill mode, and you can see that the output current waves are perfectly sinusoidal. Now, we simply go from hill to power mode. As soon as we do that, you can see that the LEDs on the gate drivers inside the hardware are blinking, which indicates that we are now working with actual Power Electronics hardware. Initially, the cutoff switch is turned off, which we will turn on. On the oscilloscope, you can see the 3-phase load currents along with the DC link for actual Power Electronics hardware. The PELab also has a number of built-in hardware protections. I'm going to demonstrate to you the overcurrent protection in action. As you can see, by default, all the protections are enabled. To trigger an overcurrent condition, we will increase the DC link voltage to increase the current above the maximum allowable range of 10 amperes. As soon as we do that, you can see that the buzzer along with the fault status of overcurrent protection shows that the overcurrent protection is taking place right now. You can see that we've moved from the power mode to hill mode again, and you can see that perfectly sinusoidal load current on the oscilloscope. We are currently working on a number of applications for the PELab system, applications such as solar grid tie inverter with MPPT boost. Subscribe to our YouTube channel or follow us on LinkedIn to get the latest update. Thank you for watching this introduction. Have a great day.
Thank you, Hamza. So, assumingly, if you are trying to develop a solar grid tie inverter using the PELab, we will be going through the following process. First, we start with the simulation. The PELab will be in hill monitoring mode. The real-time simulator will simulate the whole system and send the analog measurements to the PELab. In return, the PELab will send the overcurrent protection and overvoltage protection signals to the simulator. If we include those signals in our simulation as well, this will make our simulation identical to the hardware implementation that we will have with the PELab. Next, we will operate the OPAL-RT simulator as an RCP. The PELab will be in hill to power mode. The PWM signals will be generated by the real-time simulator and will go to the Power Electronics hardware inside the PELab. The third mode in the PELab is RCP to hell. You can use this mode to generate control signals from an RCP and test it with the simulated inverter in the real-time simulator. So once the hill validation of the RCP is done, you can also validate the RCP with the actual Power Electronics hardware in RCP to power mode. In microcontroller to hill mode, we develop the control system in the PEController and test it with the simulated inverter in the real-time simulator first. And finally, in microcontroller to power mode, we will test our PEController with the actual inverter inside the PELab. So by the end of this stage, we will have a standalone inverter in the PELab. We tried to make the PELab available in most commonly used topologies and configurations. For example, you can choose your configuration with multiple inductors, EMC filters, and relays. But the maximum number of control signals is limited to 16 channels, which means you cannot have more than 16 switches and relays combined. The rear panel can also have up to 4 voltage and 3 current sensors. Since we have 16 analog channels divided equally between voltages and currents, this will only be possible if we have unused sensors. The 6-phase configuration can have up to 2 3-phase inverters in a PELab. You can select the inverter's ratings, DC link voltage, and switching technology depending on your application. But the 50 ampere version will not use the banana connectors due to their current limitations. Also, the height of the PELab will be 8 units instead of 4 units for the 30 ampere and the 50 ampere dual inverter configurations. You can use this configuration for motor drive applications, solar inverters, and 3-phase back-to-back inverter applications. The PELab MMC configuration can have up to 4 full bridge power modules in a single PELab. And due to the large number of legs, you can use this configuration for all mentioned applications, as well as bidirectional EV charger using the dual active bridge or LLC topologies. You can also use this configuration for MMC applications and cascaded H-bridge converter applications. But the system voltage should not exceed 1000 volt due to isolation limits and for safety. The TMPC configuration can have up to 4 legs as well, but you can mix the power modules. For example, you can have 3 legs of TMPC and 1 full bridge power module. Similarly, the MPC configuration has exactly the same options as the TMPC, but the DC link capacitance and voltages are different. So we made a summary of all currently available configurations with costing, so you can easily select the suitable one for you. There are also some limitations on the maximum number of inductors and EMC filters you can have. The number of voltage and current sensors should at least cover the DC links and outputs of the power modules, so we can have over voltage and over current protection implemented on them. The PEController is also optional, so you can drop it if you do not plan to use the embedded controller. Here is an example of a popular configuration: a PELab with dual 3-phase inverters with silicon carbide switches, inductors, EMC filters, and relays. To calculate the cost, you have to multiply the number of power modules by the cost of each module. This also applies to the inductors and EMC filters. As for the measurements, we have 6 legs, so we have to use at least 6 voltage and 6 current sensors. So these are the currently available options. If you need something else, contact us and we will try to find a solution for you. Many of you will be wondering about the technical resources we have. So currently we are trying to make as many application examples as possible. Those examples will be available online soon as well. You'll also have access to the PEController embedded libraries, and we are planning to have a simplified embedded framework for the PEController. We are also planning to make training videos to help you use these resources. So now the boring stuff. Let me introduce Taraz Technologies to you. We are around 20 people, mostly engineers. We have been providing research-oriented power electronics solutions since 2012. Our products include gate drivers, power modules, sensors, data acquisition devices, and fully integrated power electronics systems such as the PELab. Our product design philosophy focuses on ease of use, research-friendly, and modular solution that can help you accelerate the R&D cycle while providing maximum versatility for your research. We are located in Islamabad, the green capital city of Pakistan. We have customers in more than 32 countries, and we are grateful to them for their trust and valuable feedback, which help us improve our products continuously. Special thanks to our PELab launch customers. If you guys are here with us, thank you very much. If you need anything, you can contact us directly, or you can contact our nearest distributor to you. It's our pleasure to serve you. So, you have reached the final slide. You must be an absolute legend. Thank you for bearing with me till the end. We would love to hear from you soon. Thanks again and have a great day.